I decided to talk about anomaly cancellation in superstring theory. And as I already wrote here, I prepared a rather extensive lecture notes and accompanying mathematical file to do some computations for you, which is available on my web page. So if you are interested, please have a look. Another thing I just noticed is that I prepared my talk assuming that the audience members are mostly young string theorists, but apparently that's not the case, right? So I need to adjust on the fly what I should talk about. I'd like to start with some questions. How many, so please raise your hand if you consider yourself mathematicians. Just not much, just a few. How many, if you think yourself physicists, could you raise your hands? So almost physicists, okay. And how many of you consider yourself a high energy theoretical physicist? And some quantum math physicists? Okay, and how many of you have Polchinski, textbook of Polchinski on your bookshelf? Many. How many of you follow the anomaly cancellation of heterotic strings if you have the Polchinski? Just very few, okay, good. Okay, then I think I get the idea. And so in my lecture notes, I started the discussion with the general theory of anomalies. But before going that, let me start with the section -1, talking about the spectrum of the superstring theory. So that's necessary, I guess, because when I talk about anomaly cancellation in string theory, you need to know what superstring theory is, right? So let me start with superstring theory. Of course, I cannot cover every detail of it, but let me just say a few words about it in order to get started. So it's a theory in 10 dimensions. For condensed matter physicists, this means 9 space dimensions plus 1 time-like dimension. And super here can mean either supersymmetry on the worksheet or supersymmetry on the space-time, but let's talk about space-time supersymmetry. And there are 2 versions of supersymmetry in 10 dimensions, and this is called, well, there are actually 3 versions, but they are called n equals 1 supersymmetry and n equals, people usually use Roman letters for some reason in 10 dimensions. And type 2a and type 2b. So these are the name of the supersymmetries. And this 1 and 2 refer to the number of supercharges. So I need to remind you briefly about the spinors of SO 9,1. So our space-time has 9 spatial direction and 1 temporal direction. Therefore, you need to consider SO 9,1. Maybe, well, if we want to be pedantic, I guess we should use lowercase letters to denote the algebra. And there are positive chirality spinor and a negative chirality spinor. So let's say this is S plus and this is S minus. And these are both real representations. So n equals 1 or type 1 supersymmetry contains just 1. 1, S plus. Well, you can take S minus instead, but it's just a difference in the convention. So you don't have to consider both. And in the case of type 2, you consider 2 supercharges, and 2A has S plus supercharge and S minus supercharge. But in the case of type 2B, you have 2 supercharge of the same chirality. So this is the choice of the supercharges. Of course, you can consider 3 or 4 supercharges in 10 dimensions. But if you do that, you will necessarily have tensor fields, symmetric tensor fields with lots of indices, and nobody knows how to do with them. If I say that, some people in our community gets angry because there are people trying to make sense of that, but well, it's very difficult. So it's useful to restrict your attention to just these 3 cases. So in the case of type 1 supersymmetry, there are 2 basic supermultiplets. One is supergravity multiplet. Another is the gauge multiplet. And supergravity multiplet, as the name suggests, contains the metric G mu nu and something called gravitino, which is a spinor with an additional vector index. And then there are a bunch of form fields, which is a higher degree differential form generalizations of Maxwell's fields. And then something called Dilatino and the dilaton. Yeah, so this is gravitino. This is dilatino. And this is known as dilaton. So this is a scalar. For the gauge multiplet, you just have gauge fields and correspond associated gaugino. So this is the gauge field, and this is the gaugino. So the interesting thing is that in this 10-dimensional n equals 1 supersymmetry, the only parameter in the theory at this level is just the choice of the gauge group G. You cannot do anything else. So in 4 dimensions, in 3 + 1 dimensions, well, our world itself is described by the standard model very well. It has a fixed Lagrangian, but you can pretend to be a god or Buddha and write down whatever Lagrangian you like and try to study what the physics it describes. But in 10 dimensions, you cannot choose there is not much freedom, even if you are a god or a Buddha, to choose the Lagrangian. And the only choice is the choice of the gauge group. So that's for type 1. In the type 2 case, the thing is even more constrained. So in both cases of type 2 and type 2b, the only thing you are allowed to have is supergravity multiplet. And nothing else. So in the type 2a case, you have metric And gravitinos, I forgot to say, is the gauge field for the local supersymmetry. That's why for one spinor, chiral spinor representation, you have alpha, and because you have a gauge field, you need an additional vector index. In the case of type 2A, with the same reasoning, you need a gravitino for S plus and gravitino for S minus. And then tons of form fields. And two sets of dilatino, and then the dilaton. In the case of type 2B, it's similar, but the two gravitino you have are of the same chirality. Again, you have tons of form fields, but the degrees of form fields are different. On one side, you have even degrees. On the other side, you have odd degrees. And you have two dilatinos and two scalars. So that's the spectrum of the type 2B supergravity. And you can do anything in these two cases. I mean, the massless spectrum is just determined by the amount of supersymmetry. So that's the situation. And here comes the tricky issue in trying to make sense of these massless supergravity spectrum. So these are chiral fermions, and I hope, as you know, chiral fermions have anomalies. So unless the gauge and gravity anomalies are canceled, it doesn't make any sense to do quantum field theory analysis with it. So the first thing you need to check is that the anomaly is canceled. So in this case, the anomaly could come from this one, the other one, this fermion, the other fermion, and the fermion here. And well, the theory of anomalies, at least at the perturbative or local level, was developed in the early 80s. And you can apply each formula separately for each of these fields. If you combine them, there's some miraculous cancellation for a very specific G, as I will explain. And that somehow involves the form fields too. And so that's called Green-Schwarz mechanism, which I will explain. But long story short, people found that with this, if you start from 10 dimension with n equals 1 supersymmetry, the anomaly cancellation requirement allows only four choices of G. 4 choices of G. So at the level of Lie algebra, the only allowed choices are U1 to 598 or U1 248 times E8 or E8 times E8 or SO32. So these 4 are the only choices of gauge group you can write just by looking at the anomaly cancellation requirement. Furthermore, if you combine the consistency of supersymmetry, transformation rules, and the anomaly cancellation, actually these 2 cases can be ruled out too. So there are really just 2 cases. Hi. The question was, when I wrote these symbols, what did I mean? either did I mean Lie groups or Lie algebras? I just meant Lie algebras here. Determining exactly, sorry, I meant Lie algebras here. Determining exactly which Lie group is the gauge group of superstring theory is a tremendously complicated question. And the final answer hasn't been written down, in my opinion. If you want to consider the interaction of center of these groups with the spin structure, and I don't know. It's difficult. We will see some part of it later. And right. So this is tremendously different from the situation in 4D. Hi. You are perfectly right. I cannot even. Yeah. Thank you. I will make many mistakes along the way, so please point them out. Right. So the situation is tremendously different from the situation in 4 dimensions, right? Here, we are wondering exactly why our world is described as SU3 times SU2 times U1. Why is it not SU5 times SU2 times U1? Nobody knows, right? Because you can write whatever Lagrangian you like with fermions, gauge fields, interactions. However, suppose we have lived in 10-dimensional spacetime and we have observed that the spacetime had supersymmetry, right? Suppose we are 10-dimensional creatures, and suppose the history of science there is so that people found this anomaly cancellation argument, and the gauge group turned out to be E8 times E8 to SO32, and that would have been accepted by derivation of the gauge group of the world if we had lived in 10 dimensions. So it's such an amazing fact to me that these consistency requirement just fixes the Lie algebra. So I'm going to tell you exactly how this happens. Going to type 2A. In this case, there's no anomaly to speak of because these are non-chiral combination. The other is non-chiral combination, and there's no problem in the form fields either. So there's not much to talk about in type 2A, well, if we don't introduce branes. In the case of type 2B, this is chiral, this is chiral. And not only that, there is one additional issue coming from something called self-dual form field. So if you study the supermultiplet structure, there is a 5-form field strength, which is something like the gauge field strength for a 4-form field. I mean, all this is very schematic, but at least at the level of the particle spectrum, this multiplet contains something like this, with the condition that F5 is self-dual under the Hodge dual in 10 dimensions. This is possible because Hodge dual square is +1 in 10-dimensional Lorentzian spacetime. You cannot do this in 4 dimensions because in 4 dimensions, Hodge dual equals -1. So you cannot restrict to the +-1 eigenspace for real fields. So this is doable in 10 dimensions, but it gives us headaches when we want to analyze its dynamics. This is because, well, standard actions of Maxwell-like fields with higher form of this form, which is FP wedge star FP, right? So this is, and you can vary the gauge potential in this Lagrangian and derive the equations of motion. However, with this self-duality constraint, at the very naive level, this is just F5 wedge F5, and because degree is odd, this is equal to minus F5 wedge F5, meaning that action is 0. So the naive action doesn't work. Of course, there have been many people trying to make sense of it, and certain sense have been made. But this at least illustrates you that there's a problem in the quantum analysis of such a field. And it turns out that such a self-dual form field also produces anomalies. And it so happens that the sum of the anomalies of Gravitino and the 5-form field and the Dilatino cancels out. So that's another fascinating feature of the superstring theory. So that's the spectrum of the superstring theory I want you to be aware of before getting into the analysis. So it's a good place to stop. And if you have any questions, please go ahead. Are you all happy with it? All right. In the rest of my talk, I'm not going to use supersymmetry at all, so you can forget about it, except for this particular spectrum of fields. So let me go to the analysis of anomalies. So let me very quickly review the modern general theory of anomalies. So as I'm going to explain, anomalies contains two parts, local or perturbative anomaly and something called global anomalies. And the theory of local / perturbative anomalies have been perfected in the mid-80s. So, or yeah, mid-80s to early 90s. So it's very well understood. But when I was a grad student, which is already quite some time ago, the general theory of global anomalies was not available. But thankfully, from about 10 years ago, or already 15 years ago, I guess, the developments in the topological phases of matter in condensed matter physics gave high energy physicists a general theory of global anomalies. So that's the good thing we currently have. So at present, we have a fairly complete theory of general structure of anomalies. I'm going to explain that and just apply that to this set of fields. So, I mean, that was a great surprise to me when it started to happen in front of my eyes. I kind of envy you guys because, I mean, the general theory is available. You don't have to worry anything. You just have to learn and apply that. So let's say you consider quantum theory T, which is a d-dimensional. So today I'm going to use relativistic convention of calling, I'm using space-time dimensionality for the dimension of the theory. So this is the dimension of the theory. And so you have, suppose you have a d-dimensional space-time, which I assume to be closed. You can compute the partition function of this theory. And very naively, you would think that it takes values in a complex number. So when you first learn quantum field theory, you learn that the partition function is a number. But then you learn that when the theory has a local anomaly, that number depends on the gauge you choose. If you do gauge transformation, this value changes. that's a very tricky way to state things, right? What is this number which slightly depends on the situation you consider, but the change is completely controlled. So a better way we now use is to say, this is not a complex number, rather it is an element in one-dimensional complex vector space. So this is a one-dimensional complex vector space, right? Without a canonical basis. So in order to convert such a thing into a number, you need to choose a basis. And you measure the number with respect to that basis. But because that basis is chosen by various conventions you make, that number itself is kind of not well defined. But as a vector in this abstract one-dimensional vector space, it's a fixed object. And what we have learned, sorry, by we, I meant all the people like me who studied quantum field theory 25 years ago, as a change in the partition function under a change of the gauge, it's just that the partition function is a fixed vector here, and the choice of the gauge chooses a different basis. And the relation between two different bases are completely determined. So that's how you have the anomaly. So, but in order to make sense of it, given a theory with an anomaly, you need a way to associate a complex one-dimensional vector space to, はい、どうぞ。The question was what I meant by giving a theory. There's no definition, and you need to live with it, unfortunately. Please come up with the minimal mathematical framework where the symbols I write in the blackboard make sense. So that's what mathematicians should do when you encounter physicists saying something nonsensical. So that's the difference between mathematicians and physicists. As you will see, without these precise definitions, we can do computations. So that's the funny part. And we will see a very non-trivial cancellation. So that's the very general attitude you need to have when you want to understand theoretical physics. But for now, by a theory, you can think of it as a way of assigning, given a closed d-dimensional manifold, an element in a complex vector space, one-dimensional. And that complex vector space is also assigned in a certain way. So if you want, you can cook up a categorical framework. So the question was whether it's okay to just think that these are given. I'm not really sure. Yeah, you really need to come up with a minimal mathematical framework in your head where what I'm going to write in the blackboard makes sense. Yeah, I can. Yeah, but I'm afraid that's the only thing I can say. So in order to, that's also how I'm trying to motivate all of these constructions. So we need to be able to make sense of this equation. Therefore, we need to have an association like this, right? Furthermore, if you have suppose you have two situations. So when I write ND, this is not just topological manifold, but plus smooth structure and spin structure, and maybe G bundles. plus connections. So I'm using a single letter to denote all these combinations. And in order to describe gauge dependence of the partition function, you need to be able to compare VND and VND prime for two different NDs. It can happen that two different NDs can share underlying topological manifold and the principal bundle. So it can share topological manifold and topological principal bundle, but can have different metric plus connections, right? In these cases, we need a way to compare element here and element in there. Otherwise, you cannot study how the quantum field theory you are interested behaves when you change the background metric or background gauge field. So just saying that the partition function is an element in a complex dimensional, so one dimensional complex vector space is not enough. You need to have a way to compare these things when these additional data are different. So you need to be able to compare such two NN. So that's the traditional, that's so-called traditional anomalies. But if you'd like to do quantum gravity eventually, you need to be able to sum over all possible manifolds. So that's not necessary if you are not trying to do quantum gravity, but if you want to do quantum gravity, then you need to be able to compare these two vector spaces and elements in them in such a case when these two NDs don't share underlying manifolds or underlying principal bundles, because you need to sum over it anyway. So what you need to do have is that suppose ND and ND prime are related in some way, then you need to have a unitary operator comparing the two vector spaces. So what do we mean by two related NDs? So I don't think there's any a priori way to say what should be the correct concept, but the consensus at this moment is to consider the Boldism between two NDs. So here you have ND and you have ND prime, and you can have various things going on. If you have principal bundles, you can have various non-trivial topology of the principal bundle on top of it. So all these data is considered as a way to relate ND and ND prime. You can think of it as a off-shell quantum gravity process if you want. So what you'd like to have is a way to create a unitary operator comparing the incoming boundary and the outgoing boundary over Boldism. So coming back to what we started the discussion, in order to talk about the anomalous theory, you need to have the following machinery. So one is a way to assign one-dimensional complex vector space for each closed d-dimensional manifold. In addition to that, for each Boltzmann connecting to such d-dimensional closed manifold, you need to have a unitary operator comparing the one-dimensional vector spaces and satisfying various other consistency conditions. So such a data, U and V, such data are provided by d+1 dimensional invertible QFT, which I write by A because it governs the anomaly. So A depends on T. Hi. The question was why I chose the letter V and I chose the letter U. The answer is just it's a convention. Yeah. Are you a man who writes the set of map between two sets, set AB? If so, it's a home set in the category, right? If you are very strict about notations, then you will use, the same letter for everything. But in physics, it's conventional to use various different letters for different objects associated with a single functor. So yeah. Another thing is that these days, I'm not sure what is the definition of your PQFT. Here, these are not PQFT in the standard sense because it depends on the metric and connections, not just, yeah, so. Yes. I don't know. Maybe it's not. So the question was why we need unitarity here. I don't know. For the cases we use, they are all unitary. We may get something more general by dropping this condition, but I think having unitary maps is enough. Right. Right. Yeah. So today I'm going to just discuss unitary theories. Hi. The question was, when the theory actually depends continuously, etc., on metric, is it still a functor from a Boltzmann category? The answer is no. You need to have a concept of functor with smooth data put in. So you need to be able to say smooth family of objects and smooth family of functors depending on the objects. But the theory is already there, if I remember correctly. So Omori-kun knows much better than I do, so you should ask him. So the theory of invertible QFT in the mathematical sense is basically done, I think. So but that only gives you this thing and the other thing. And in order to talk about the anomalous theory itself, you need to go down one step further. And I'm not sure whether the mathematical framework is completely settled at that level. But today, I only deal with invertible QFTs. So maybe that might be enough. Hi. 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 The question was whether it's okay to think of them as the line bundles over the moduli space of geometric objects. That's kind of okay as far as the continuous part is concerned, but there are much more discrete data you need to put in. So I don't think just saying that we are characterizing line bundles on the modular space is enough. So in the past, if you read papers on anomalies in the late 80s, that's what people said, but that's not enough. For example, if you consider anomalies of a finite group, then all of the data you have are just, I mean, if you are very naive, the moduli space of G connections on a manifold with finite group G is just a discrete points, right? So there's not much information on line bundles on it. Of course, there are ways to make the structure much more, categorical or local, so that by putting scare quotes everywhere about the moduli space of finite group bundles over and line bundles on it, then everything is okay. But the vanilla definition of line bundles, etc., do not work. But in any case, this is more or less settled. You can go to the literature and learn it. Yeah, the question was why I said invertible. I realized that I didn't explain the word invertible. I blame you guys for asking many interesting questions, by the way. But, by invertible, I just mean the condition that all of the Hilbert spaces, vector spaces associated to one d-dimensional manifolds are one-dimensional. That's the source of invertibility. General QFTs are worse. I mean, what physicists call PQFT is basically those where V of ND are finite dimensional. And more physical QFTs typically have infinite dimensional Vs. And this is one-dimensional QFTs. So, I mean, from mathematical point of view, invertible QFTs are the simplest QFTs. It's like studying line bundles compared to considering finite dimensional vector bundles before talking about Hilbert space bundles, right? So, I mean, if you are a mathematician and you are forced to study QFT by somebody, then the first thing to be studied are the invertible QFTs. But somehow nobody thought of doing that until 10 years ago or something. So, but that's how it arises. Those. The question was exactly which space-time structure it depends on. I didn't specify. So in order to talk about it, you need to talk about exactly which data on the manifold you want to impose. So there are theories which depends on Riemannian structures. Yeah. Or you can go to the other extreme. You can, I think, consider invertible QFTs defined on just topological manifolds, including the ones which don't have smoothness, for example. I don't know what kind of physical application it has, but the framework should be flexible enough to allow for whatever space-time structure you can think of. Yeah. So now we need a way to characterize such a invertible QFT. I introduced lots of data, right, B and U. So an invertible QFT determines all these things, satisfying complicated conditions. But it is believed that they are characterized, essentially uniquely characterized by the association Z of A, which is a map from MD. Oops, I shouldn't use this line. This is supposed to be the line. So the anomaly theory or invertible theory is supposed to be characterized by the association to MD plus 1, which is the partition function, where this is closed without the boundary. And here, this is really canonically a complex number. So that's an important point. I should say it's really just U1 value. It's a very non-trivial statement. I don't know the proof, but it is believed. So instead of trying to characterize, I'm trying to give all of these data, U and V, you just have to give this assignment. So that's a very nice statement if true. A very readable account of why this is the case was provided by Yonekura-kun. Proof by Yonekura for invertible TQFTs, where there's no continuous dependence involved. It's cited in my lecture notes on the web page I wrote. So you can reconstruct all of the necessary functor just from this data. You need to make tons of choices along the way to construct U and V, but you can show that all the functors you can get in such a way are actually the same, equivalent. So we need to have such an association. And furthermore, it is known, it is believed, it is proved, I guess. Suppose this closed manifold MD1 D plus 1 is a boundary of another manifold. In this case, suppose, then we have the formula that MD plus 1 is equal to exponential of 2 pi I times integral of over LD plus 2 over certain differential form. Differential form representation of some characteristic class. So of some degree D plus 2. So this P is known as the anomaly polynomial. So if you expand the definitions concretely and apply to the case when the variation of the gauge fields, etc., are very small, then you reproduce all the nice geometric analysis done in late 80s about anomalies. But this is formulation which also captures all the global anomalies. So these are the general theory. So let's say T is a d-dimensional chiral fermion. Taking value in the, say, positive chirality spinor, tensor V, of this V. Well, I shouldn't have used V. I blame alphabets having so few letters. Let's use W, I guess. So this is complex vector bundle with connections. So classically, you say that the chiral fermion is a section of a spinor bundle tensor with some complex vector bundle with connections. Corresponding anomaly theory A has this partition function, which is just exponential of 2 pi I times the eta invariant of the Dirac operator associated to spinor bundle tensor, the same complex vector bundle. So that's the situation. Oh, sorry, I forgot to say one important constraint coming from it. I'm very sorry. I forgot to say one thing. Here, for a given D plus 1 dimensional manifold, there can be two different extension to higher dimensional manifold. So let's say this is M and this is L. This is M and this is L prime, which means that this should also equal to exponential of 2 pi I integrated over LD, L prime of a similar characteristic polynomial, right? But there's a priori no reason why this and that should be the same. So you need a condition that integral of P over L minus integral over P over L prime is in integer. So this is a required condition, right? For exponential 2 pi I times something is equal. This can be characterized by considering the manifold you get by pasting the orientation reversal of L prime to L along the shared boundary, because this is equal to the integral of this anomaly polynomial over the closed manifold L. So this anomaly polynomial has a feature that its integral over a closed manifold is an integer. So that's a quantization condition. Coming back to the discussion, I'm sorry for the mistake I made in the ordering of the content. So I was talking about chiral fermions in D dimensions, taking values in, say, positive chirality spinor times a complex vector bundle with connections. Then the corresponding anomaly theory is a D plus 1 dimensional theory whose partition function on a closed manifold is an exponentiated eta invariant. The question was to explain this better. So let me try. So we want exponential 2 pi I over LP equals 2 pi I over L prime P. So we want to understand what this means, right? So this means that LP minus L prime P is in Z, right? Now, then you can reverse the orientation, which changes the sign here. And once you reverse, you can glue them. Yeah. Please ask any questions. So this means that the integral of this needs to be Z. When I gave this type of talk a long time ago, people asked me saying that, do all closed manifold LL appear in this way, right? So that's a good question. If only some L curly L's appear in this construction, yeah. That's the question. So the point is that as L prime, you can choose something like this, some disjoint union of the original one with some additional curly L. Then if you do the same construction, this part just becomes this. So you really need to impose this constraint. Now, suppose MD plus 1 is a boundary of LD plus 2. Then the APS index theorem says that this is equal to exponential of 2 pi I integral over L of A hat genus, which depends on the curvature, right? Times the Chan character constructed from the gauge bundle. So R here, the space-time curvature, Riemann curvature. And this F is the curvature of the vector bundle. Connection. And I'm going to tell you what A hat is. Chan character is a trace in the representation W of exponential of IF over 2 pi. So that's it. So this means that the anomaly polynomial P for such a theory is just A hat R times Chan character F. So this is for complex fermions. Sometimes you can impose reality condition on chiral fermions. So these are called Majorana spinors. In that case, the anomaly polynomial gets an extra factor of 1/2. So that's the anomaly. Finally, so these are anomalies for the chiral fermion, but we need to deal with gravitinos. So gravitinos are like spinors with additional vector index. So gravitinos are sections of S plus tensor T and D. I mean, tangent bundle of your manifold you are thinking of. So the anomaly theory, corresponding anomaly theory, is given by exponential of 2 pi eta of D slash, which is the Dirac operator's S tensor T n, but n is no longer there, right? So you need to use m. So in order to take into account the dimensional difference, you need to subtract 1. So this is a formal difference of vector bundles. So you need to subtract 1. But actually, you need to subtract 1 more. So this is, and I think I need 1 two closing parents, and also I here. So this is to remove one additional direction in M compared to N. And additional R is to remove gauge degree of freedom. So you need to subtract 2. And the anomaly polynomial for this theory, is when MD plus 1 is partial LD plus 2, it's equal to exponential 2 pi I integral over LD plus 2 of A hat genus times the Chan character of the space-time curvature itself, but you need to subtract 3. What happened was that there are 2 subtractions. One was between one additional direction between N and N. Another one subtraction was from gauge degree of freedom. Here we are doing the computation in L, which is 2-dimensional higher than N. So you need one more subtraction. So that's unfortunately very complicated. This is it. どうぞ。はい。
同じ P のじゃなくて、普通のフェルミオンだった場合は、
はい。
ドメインオールフェルミオンとかで理解して、なんか、水的にエータになるなみたいな、水点4に比べるわけじゃない。同じように、グラビティの場合も。
The question was how we can derive this from physics perspective. So for fermions, you can consider domain wall fermions and derive this physically. I think it's very difficult because you need gravitinals. Is it really consistent if you start considering local supersymmetry variation? Maybe it is. I don't know. Kantaro says that there shouldn't be any problem. I haven't thought about it very carefully, so so I mean, yeah. What bothers me is that you need to forget about supersymmetry to do this computation, and that sounds a bit tricky. I don't know. Yeah, maybe I don't know. That's a very good question. So these are the so these are enough to compute anomaly polynomial and check the local anomaly cancellation for type 1 theory. There's one more ingredient. Type 2B 5-form field. So this is self-dual field. So such a field can be considered in any dimension D, which is of the form 8K plus 2. And the trick is to relate this condition to signature operator. Signature operator is, well, basically the register, acting on the sum of all of the differential forms. So in the case of fermions, the split of fermion to positive chirality and negative chirality part is done by a chirality operator, and instead you need to use signature operator. And I don't have the time to explain the subtleties involved, but mathematically, there is an invertible phase which is of the form exponential, associated to the signature operator. So let's call the say sigma, which is exponential of 2 pi I of the eta invariant associated to the signature operator. If you go back to the original papers of Atiyah, Patodi-Zinger, this is the first operator they discuss. So this is a very well-defined thing. And you can show that it satisfies the same type of formula where this L is not the Hiltzev L genus. So this is clearly very well related to chiral form fields, but there is a catch. So this is a well-defined invertible phase in any mathematical sense. But the anomaly of self-dual form fields were computed by Alvarez, Gomez, and Witten, I think, in the late 80s. And their perturbative Feynman diagram computation, and I didn't explain anything about how to compute this anomaly polynomial from Feynman diagram computation, but it can be done. Feynman diagram computation of anomaly polynomial of self-dual form fields. If you are very careful about the overall normalization, is 1/8 of L. Which is a shocking fact. So naively, you would like to have the anomaly theory to be 1/8, eighth root of this, but you cannot take eighth root of a U1 valued function consistently. You can't generally take 1/8 of an integer or a U1 valued thing consistently. For example, you can find a manifold on which this integral of this is not in Z. Of course, 8 times the integral of L is an integer because it's a signature, But if you divide by 8, it does not hold. So this is the main issue of making sense of self-dual form fields. There are tons of confusing issues, which I'm going to cover in the second part of the lecture in the afternoon. But for now, please accept that this is the anomaly polynomial, which you can make sense after a long analysis. Let's accept that. So now I explained all of the ingredients to check the local anomaly cancellation. So let's say you want to consider type 1, say SO32, right? So what you need to do is the contribution of, first of all, the gravitino. Let's start from SO32. So let's remind ourselves that you have SO32 gauge field and the super partner, which are the gauginos. So these are adjoints of SO32. So this contributes by, and they are measured on a while, so you need 1/2. They have R. And Chan character is the trace in the adjoint representation of exponential if over 2 pi. So this is what you need to compute, and you just need to take the 12 form part. And you need gravitinos and the dilatino, right? So I said that I need to add the gravitino contribution, which is a trace in the vector representation. I mean, SO, as we are 2-dimensional higher than 10-dimensional spacetime, we effectively need 12-dimensional representation of the spacetime curvature. And you take this. And as I said, to get the anomaly polynomial for gravitino, you need to subtract 3. And because you have dilatino, which happen to have an opposite chirality, you need to subtract 1 more. So you need to compute this and take the 12 form part. So this is what you need to compute. And you might hope that this is 0, but not quite. But there's a drastic cancellation. So I want it to be practical in this set of lectures. So far, I explained the various abstract things and abstract formulas. So this is concise, but you might not yet know how to compute them, right? I will tell you how to compute it, and I will compute it on my laptop, show it to you right now. So the good thing is that these characteristic classes can be computed using something called splitting principle. So splitting principle means that you can pretend every vector bundle appearing there as a direct sum of line bundles. So let's start with the tangent bundle. So let's complexify it. And you pretend that this is a sum of LD plus 2. And we write Chan characters. Sorry, so these are complex line bundles. So you have first Chan classes. And because we start from SO bundle, Chan classes, first Chan classes appear in pairs of plus and minuses. And the Pontryagin class Pi is defined to be symmetric polynomial. So elementary of xi squared. Yes.どういうことでしょうか。はい。はい。はい。SO10 だからですか。いやいや、so the question was what this SO12 is. So you see here you have 12-dimensional manifold together with a SO32 bundle. So you have SO32 and also SO12 involved if you use wick-rotated Euclidean spacetime. So this is for spacetime curvature, and this is for the adjoint of SO32. So it's not that I'm taking the subgroup of SO12. I mean subalgebra SO12 or SO32. Yes, we assume that the 12-dimensional manifold is not just oriented, but has spin structure. Yeah. So the question was, what is -1? So this is the contribution of the gravitino. The last contribution, or maybe I should have written instead as -1/2. So this is the gravity. This is a Diratino contribution. So this is the gravitino contribution. So this is the gaugino contribution. Thank you for the question. そうです、そうです。Yeah, you need to learn superstring theory or representation theory of super algebra in 10 dimensions to know that the chirality of Diratino and the gravitino are opposite to each other. So A hat is defined by the sum over product over i's of xi over exponential of xi minus exponential minus xi. And you can rewrite it, you can expand it and use this definition and conclude that this is P1 over 24 ... So that's the complicated computation. Similarly, if you want this, trace in the SO12 of IRO2 pi. This is just sum over I of exponential xi plus minus xi. Right? Also, we need to decompose this 32-dimensional real bundle into line bundles, let's say twiddle. And then call the first chunk class as y1 minus y1, y2 minus y2, ... Then you need to compute the Pontryagin class of those. To distinguish them, let me just call them Qi. So these are symmetric polynomial of yi squared. Then trace of adjoint of SO32 of exponential of f over 2 pi is just the sum over I larger than j of exponential of yi plus minus yj plus minus. plus 16, sorry. So these are for the Cartan subalgebra, and these are from roots. So for each ordered pair, you have 4 terms. So you multiply. So these are enough to plug in. So after, I think last 10 minutes is just exactly the right amount of time to show this to you. So let me try connect to hi.よいしょ。よいしょ。ちょっとお待ちください。これを止めないとハウリングが。Okay. So let me share the screen. Can you see it? Well, そのパソコンがつながってたんですよね。それつながないとそりゃデータはいかないやっていう。朝はつながってたんですけどね。飽きまへんか。オプションでミラーリングとかなんかあると思うんですけど。こっちの画面には出てるんでしょう。いや、この画面ごと、この画面ごと持ってきゃいいので。環境設定が。IT じゃない。ミラーリング。ミラーリングが出てこない。これにしてみる違うな。これはでも今この MSD なんとかになってるんですよね。ちょっと前。映った。いや、単にウィンドウを。皆さんログインなんで、ズームに入ってみた方が良かったかもしれない。Sorry for the mess. 普通にそこで最大化すればいい。ああ、はい。OK, I need to go back to English. Can everybody? Can everybody see it? In view of time, let me start. So, as I said, A roof genus is a product of x over exponential x over 2 minus exponential minus x over 2. Apparently, I forgot to put x over 2 in the blackboard. あれを消すのは僕にはできないな。Thank you. So this just expands this function in terms of x to some order 10, say. And we are going to consider elementary symmetric polynomials of x squared, but Mathematica cannot directly construct elementary symmetric polynomial representations of x squared. I need to replace x squared by, say, w. So I just replaced x squared by w. With t is a dummy variable to count the degree. And you need to multiply them, let's say 5 of them or 6 of them, right? So I replaced w by yi. So yi here is xi squared. Mathematica has a function which converts a symmetric function of, say, y1, y2, y3, etc., into elementary symmetric polynomials. So this is the function. So I just convert this product into an expression in terms of Pontryagin class. So you get this. So this is the computation of the A hat genus from the definition, kind of. So you see that the leading term is 1, of course. Then the next term is minus P1 over 24, which is the famous first contribution. And then 7P5, P1 squared over 5760 and minus P2 over 140, blah, blah. So we can just do the same thing for any other parts. So let's consider Chan character part. So it's based on exponential x plus exponential minus x. So again, we just compute the expansion, replace x squared by w. And in this time, instead of taking the product, we sum them. I guess I should show it. It's just a complicated expression, and you can convert it to Pontryagin classes as before. Somehow, when I created this Mathematica notebook, I used dimension 20, which was wrong. But in the end, only the constant term changes, so I'm cheating it. And I just changed the leading dimension to whatever necessary. The next thing is to compute the Chan character in the adjoint of SO32. So as I said, it's for SO32, it's rank 16 plus the contribution of the various roots. The roots of SO even is plus plus, plus minus, minus plus, minus minus for all of the ordered pair. So this is the adjoint contribution. So the SO32 contribution is, I combined all of the steps into one long line of Mathematica code. So I replaced z squared into w and etc. And then we convert w into symmetric, elementary symmetric polynomial, which is a Pontryagin class of the gauge bundle. So this is the SO32 contribution, right? here I'm doing this for E8. E8, we need E8 times E8. E8 has a SO16 subgroup, and a joint of E8 decomposes as a joint of SO16 plus positive chiral spinner of SO16. So the joint contribution can be computed by the same formula, and we need to add the spin contribution. To compute spin contribution, you need to enumerate all of the weights of the spin contributions, and I'm not going to explain what I'm doing here, but you need to generate 128 vectors, which are weights of spin representation, and you compute the Chern character in that representation, and this is what you get. And E8 adjoint is this very nice function. You see, the adjoint of SO16 has Q1, Q2, Q3, right? This is because in SO16, I mean, classifying space of SO16, there are Pontryagin classes of degree 4, 8, 12. But if you compute the E8 adjoint contribution, Q2 and Q3 are gone. This is because on the classifying space of E8, the first element in the integer cohomology is Q1, which is degree 4, but the next contribution is in 16 degrees. So it's perfectly sensible that Q2 and Q3 disappeared by summing the contribution from SO16 adjoint and SO16 spin. And we need E8 times E8, so I just use R1, RIs. So the question was why I chose SO16 to do the computation. You can, of course, enumerate all 240 roots of E8 and sum over them. This is just the same as generating all such roots by decomposing into SO16. It's just a way of computation. There is a very deep reason. So the question was whether there's a deep reason or not. But I think the fact that E8 has the maximal rank subgroup SO16, such that the adjoint plus spinner is of the smaller group is the adjoint of a larger group, has a very deep meaning, in my opinion. I mean, that depends on your opinions, but yeah. I just want to be practical. So I wanted to show how it can be computed. I mean, if you can type in all of the 240 root vector coordinates by hand, please do that. That suffices. This is one way to do this. Okay, so the Gaugino contribution is 1/2 A roof or A hat times SO32 adjoint, right? So this is the horrible contribution of the anomaly polynomial of the adjoint of SO32. If you want adjoint E8 times E8, you get equally horrible expression, right? Now let's go to the Gravitino-Dilatino contribution. So as I said, it's 1/2 A roof times Chern character for the 12-dimensional vector representation minus 4. As I said, minus 3 is the Gravitino contribution, and minus 1 is the Dilatino contribution. So this is it. So let's see what happens if we add all of the fermion contributions. Adjoint of 32 and Gravitino, Dilatino. Let's simplify. So the sum of all of the anomaly polynomials is not 0, but you see a factorization. And once the anomaly polynomial is factorized, there is something called the Green-Schwarz mechanism, which allows us to cancel it, which I will talk about in the second half of the talk. And similarly for adjoint E8 times E8, you have this factorization. So what was noticed already in the very early paper, almost the first paper by Green and Schwarz, is that they noticed that this factorization happens only for SO32 and E8 times E8. I don't know how they checked that, they never explained it. It's also written in Green-Schwartz written. They never explained that either. I wonder how many of you encountered that sentence in the textbooks or original papers and try to check whether there are no other possible gauge groups. Because, you know, if you don't trust them, maybe there's still one additional strange group where this factorization happens, right? Then you are as great as Green and Schwartz. You would have found another consistent supergravity theory. So when I had a summer intern 10 years ago, I suggested him to do the classification. So he laboriously went through all of the algebras of dimension 496 and checked that indeed these are the only two cases where this factorization happens. So this is really it. And finally, let's discuss the celestial form field contribution. So again, L polynomial can be computed in the same fashion. I mean, the trick is always the same, right? So this is the L polynomial of Hirzebruch. But the point is that the 5-form contribution is 1/8 divided by 8. And in this case, you need to compare, add the 5-form contribution and the 2 sets of Gravitino and Dilatino, because we are talking about not type 1 theory, but type 2 theory. And in this case, you get 0. So you have perfect cancellation. So that's the first half of my talks. So thank you very much.
Thank you for the very great talk, lecture. And is there any question or comments? なんか質問があったら。
何でもどうぞ。はい、後ででも大丈夫ですので。
I guess no, okay.
We can see infinity.
Great. Okay. Okay. It's that time. Okay, that's all.
Okay.
Thank you very much. And
the
last half talk is started from the 1 p.m. I think. Okay, thank you.
どうもありがとうございます。